We're going to look at another demonstration of our overcurrent protective relay demonstration system, focusing on the Schweitzer SEL-501 overcurrent relay. Now, to test this relay, we need a load that draws sufficient current, and we have just the load over here to the right. It's a shop vacuum cleaner, and we've measured the parameters in this vacuum cleaner. When it's in the running mode, it draws about 6 amps of current. When you start it up, it has an inrush current of about 18 amps for a very short amount of time, just a few cycles. Now, bear in mind that our current transformer ratio in the system is 20:5 or 4:1. So as the motor draws 6 amps of current as it runs, that's about 1.5 amps of secondary current out of the CTs to the relay. The inrush current here, 18 amps, going through the 4:1 CT ratio, turns into about 4.5 amps secondary current to the relay. The secondary current values will become important to us because that is how we program the overcurrent relay. We program it based on the number of secondary amps. So, what we're going to focus on right now is the time overcurrent feature, which is ANSI code number 51. And it has some parameters in the relay which we're going to program. 51 pp is the pickup value. This is the number of secondary amps we must exceed before this element begins to time. And this is similar to the wheel rotation of the old electromechanical relays, where if you exceeded the pickup value, it would overcome the torque, the restraining torque on that wheel, and slowly rotate the wheel until contacts would touch. Well, with the new relay here, we don't have a wheel, we don't have moving parts or anything of that nature, but what we do have is a microprocessor that's able to very accurately time the same mathematical function. So we're going to program in a pickup value appropriate to this vacuum cleaner. We're going to select a time curve, and then we're going to set the time dial setting, and then use this formula to detect, or to calculate, I should say, when the relay should trip out the breaker. So first, our pickup value. I'm going to go into the menu where we set these parameters. I'm going to set passcode to gain access to these. And I'm going to look for the parameter 51 pp, which is the pickup value for the overcurrent, the time overcurrent function. Now currently it's set to 3 amps, 3 secondary amps. Recall that our CT ratio is 4:1. That'll be 12 amps for our vacuum cleaner. Now also recall that our vacuum cleaner draws about 6 amps. So on this setting right here, the pickup value is set too high for the time function to begin picking up on the normal draw current of that vacuum cleaner. We're going to lower this number so that it will begin to time on the typical current drawn by the vacuum cleaner. Normally we wouldn't do something like this. Normally we want the overcurrent relay to trip only in a true overcurrent condition. But just for the sake of demonstration, we're going to use the normal current drawn by the vacuum cleaner to time this relay. So here's what we're going to do. We're going to take this parameter right here and we're going to adjust it down to 1 amp. Remember, that's 1 amp secondary, which is 4 amps primary, 4 amps of current to the vacuum cleaner. And the vacuum cleaner normally draws 6 amps, so this will be a low enough pickup value that our vacuum cleaner will cause the function to begin to time. Curve is U3, which according to the code in the Schweitzer manual, that is the very inverse curve according to the US standard, and it follows this formula right here. Then I'm going to go down one more parameter, and our time dial setting, which is equivalent to the resting position that was the time dial in the old electromechanical relays. This time dial setting is at 3 seconds right here, and so according to this formula, 3 will be the value of that number, multiplied by this quantity right here is going to tell us how long it will take for the relay to trip. Now the only other variable in this formula is M, and M is the multiple of overcurrent. So that's how far over and above the pickup value your actual current is. Now recall, we've got our pickup value set at 1 amp secondary. Or if you want to think in terms of primary amps, that would be 4 amps going to our vacuum cleaner with a 4:1 CT ratio. So if our pickup value is at 4 amps primary, and our vacuum cleaner draws about 6 amps primary, that means the value of M, the multiple of pickup value amps, would be 6/4, or 1.5. In other words, the vacuum cleaner, as it runs, will be drawing 1.5 times the pickup current value. And that number right there is what goes in this formula, and we'll calculate the trip time. So, time to get the calculator out. So over here, here's my trusty calculator. And I'm going to take 1.5, which is my M value. I'm going to square that, and I'll subtract 1. That right there gives me the denominator of that fraction. I will divide by 3.88, and I will invert that to get the value of that whole fraction, 3.104. I'll add to that 0.0963 to get the value inside the parentheses. Then I will multiply by the time dial setting, which, as you recall, was 3 times 3. So according to this, it should take about 9.6 seconds for the relay to trip based on the constant current drawn by the motor as it's running of 6 amps with a pickup value of 4 amps primary, a U3 curve, and a time dial setting of 3. So let's give it a test. What we'll do at this point is we will continue going down through our parameters here and save those changes. So now we're ready to do our test. What I'm going to do is go turn the vacuum cleaner on while I start my stopwatch, and we'll see how close we come to 9.6 seconds. Now bear in mind, this is not going to be a very accurate test because when we start the vacuum cleaner, we have that high inrush current of about 18 amps primary. That much larger current is going to cause that mathematical algorithm to time faster. Or if you want to look at it from the old electromechanical perspective, that inrush current would cause the disc to start to rotate faster, and then the disc would slow down as the current falls to the normal 6 amp primary value. So that's going to accelerate the time a little bit and cause it to trip sooner than 9.6 seconds. But because the inrush doesn't last for too long, that's not going to be hugely off of the 9.6 second mark. We'll just have to see how close we get. So coming over here, I'm going to turn on the vacuum cleaner at the same time I start my stopwatch. We'll wait and see how long it takes for the relay to trip it. So I wasn't exactly quick on the button there, but let's say about 8.5 seconds. We predicted 9.6. Remember that the time was accelerated a bit because of the inrush current and its effect on that mathematical algorithm. But it does at least show the concept of a time over current trip. And sure enough, our relay is showing us over here, relay X, phase B, which is the only phase we have wired up. We had a time over current event. Okay, so at this point what I'm going to do is reset my stopwatch. I'll come over here and turn the power switch off and go ahead and reset my breaker. I'll then push the target reset. So we're back to our normal display here. What I'd like to do now is put in a different pickup value in our equation. Recall that the pickup value was the amount of current we had to exceed before we overcame the imaginary torque setting in there, the restraint setting, and began to actually time in our function. So let's go ahead and change that value. I'm going to go into the set menu again, relay X, passcode 501. And what I'm going to go down to is 51 pp, the pickup value again. There we go, 51 pp. We had it set for 1 amp secondary, which, as you recall, is 4 amps primary current to the vacuum cleaner. What I want to do is actually set this to 1.25. I'm going to set for a slightly higher pickup value. So I'm going to go there, 1.25. Now 1.25 amps primary, sorry, 1.25 amps secondary. This is a secondary current coming out of the CT. Remember that the CT ratio is 4 to 1. The 4 times that gives me a primary current of 5 amps. So our pickup value on the primary is 5 amps. Our vacuum cleaner, as you recall, draws about 6 amps, and so we are not quite as far above the pickup value as we were before. This will cause the time function to take longer. It's less severe of an overcurrent condition according to our settings, and therefore the relay will give it more time before it trips out. So I'm going to save these values here. There we go. Now I need to get my calculator and predict roughly how much time that should take. So back with this. M squared, recall that M is the multiplier of current, how far above and beyond the pickup value our current actually is. So remember that our vacuum cleaner draws about 6 amps, and our primary pickup value of current is 5 amps. We had 1.25 entered in for 51 pp. 1.25 times the CT ratio of 4 gives us 5, so our primary pickup current value is 5 amps. If we do that, we get a 1.2 for a value of m. We then square that, subtract 1. I'll divide by 3.8 and invert that to get the value of this fraction right here, which is 8.8. I'll add to that 0.0963. That's the value of the entire quantity inside the brackets. Multiply by the time dial setting, which you recall was 3. And we get, lo and behold, 26.74 seconds. This should take almost half a minute before it trips, because according to our new pickup value, it's not as severe of an overcurrent condition as it was before. So let's give it a test. All right, come over here. I'll get my stopwatch ready. I'll turn on the vacuum cleaner and start my stopwatch, and we're looking for roughly 26 seconds of time before it trips. So a little bit, perhaps under 25 seconds. There's some time delay in me pushing the button. Once again, the calculation is going to be off for a couple reasons. For one, when I turned on the vacuum cleaner motor, there's that large inrush current, which is going to cause the function to time faster than we would predict at a constant draw of 6 amps. Second is the fact that when I say 6 amps at the vacuum cleaner, that's only approximate, and that does vary over time. This is not a steady load. So given those approximations, it's not surprising to see a little bit of error. But you can see, qualitatively at least, that by elevating the pickup value inside the relay, we have caused the mathematical function to give us a longer time delay, so it takes longer to trip because it doesn't look like as severe of an overcurrent condition. So there we go, a demonstration of time overcurrent tripping on the Schweitzer SEL-501.